Everyone, and welcome to another deep dive. Today, we're going small, really small. We're diving into the world of electrons.
Oh, yeah,
You know,
electrons.
those tiny particles that are always at work, even though we don't always see them.
Right, they're kind of the unsung heroes of the universe.
Exactly. We've got tons of research lined up, historical accounts, even some mind-bending physics.
It's gonna get a little weird.
Oh, it definitely will.
Yeah.
Get ready to have your mind blown wide open as we uncover the hidden wonders of these tiny but mighty particles.
You know, it's truly fascinating how much we just take electrons for granted.
I know, right?
I mean, think about it. They're literally the force behind so much of our modern world.
Yeah, from the electricity powering our homes to all the tech we can't live without.
Exactly.
It's like this whole invisible world shaping our reality.
A hidden universe.
So before we get ahead of ourselves, let's start with the basics. What exactly is an electron?
So in the simplest terms, an electron is a subatomic particle, one of the fundamental building blocks of all matter.
Okay.
It carries a negative charge and has an incredibly small mass. I mean, incredibly small.
How small are we talking?
One of the sources we looked at had this analogy that really blew my mind.
Okay, I'm intrigued.
They said if a proton were the size of a baseball, an electron would be smaller than a grain of sand.
Wow. That's mind-bogglingly small.
Yeah.
It's amazing that something so tiny can have such a huge impact.
Right.
It's pretty incredible.
So when did we first figure out these tiny things even existed?
Well, that takes us back to 1897 with a physicist named J.J. Thomson and his experiments with cathode ray tubes.
Ah, yes, Thomson's famous experiments. I remember reading about those.
Oh, yeah.
He was using these vacuum tubes with a beam of what they called cathode rays back then.
Right.
And by applying an electric field, he noticed the beam bending towards a positively charged plate.
Uh-huh.
That bending made him think that the rays were made up of negatively charged particles,
And he called them corpuscles.
which we now know as electrons.
Big deal.
So that was a pretty big deal,
Yeah.
right? Oh, absolutely. Groundbreaking. Before that, the common thinking was that the atom was indivisible, like the smallest possible piece of anything.
The end of the line.
Exactly. But Thomson's work shattered that idea. It showed us there were even smaller particles within the atom.
Talk about a paradigm shift. So Thomson really set the stage for how we understand the atom today. But things get a little weirder from here, right?
Oh, yeah, much weirder.
We have to talk about wave-particle duality, right? This idea that electrons can act like both particles and waves.
Yep, one of the most mind-bending concepts in all of quantum mechanics.
Yeah, my brain's already starting to hurt.
Basically, electrons can act like particles with a specific location, but they can also act like waves spread out over space.
So which is it? Particle or wave?
That's the thing. It can be both, depending on how it's observed or the experiment you're doing.
So it's not an either kind of situation.
Not at all. It's a both hand, which is kind of hard to wrap your head around.
Yeah, I can imagine. Do you have like an analogy or something to help us visualize this?
Sure, one way to think about it is to imagine an electron as a tiny tennis ball that can also act like ripples on a pond.
Okay, that's kind of helpful. I can sort of picture that.
And the classic experiment that demonstrates this is the double-slit experiment.
Oh yeah, I've heard of that one.
You send electrons one at a time through two slits, and even though they're individual particles, they still create an interference pattern, like waves.
It's almost like they're messing with us, changing their behavior depending on how we're looking.
It is strange, right? But it's this duality that's crucial to understanding how electrons behave and influence everything around us.
Okay, so we've got these tiny, almost shape-shifting electrons.
Mm-hmm.
But where do they actually hang out within an atom? I learned about electrons orbiting the nucleus like planets around the sun.
Oh yeah, the old planetary model proposed by Niels Bohr. It was a good starting point, but thanks to quantum mechanics, we now know that's not quite right.
So scratch the planets orbiting the sun idea. Got it. So where are they?
Electrons exist in these regions of space called orbitals.
Orbitals. Okay.
Think of orbitals like probability clouds. They tell us where an electron is most likely to be found instead of pinpointing an exact location, which is impossible because of the Heisenberg uncertainty principle.
Quantum mechanics always throwing a wrench in things. So it's more about probabilities and likelihoods than fixed orbits.
Exactly. Electrons are keeping us on our toes.
And you mentioned these orbitals have specific shapes and energy levels.
Absolutely. These probability clouds, these orbitals, they have specific shapes like spheres, dumbbells, and even more complex forms, and they occupy distinct energy levels.
That sounds pretty important.
It is. This arrangement of electrons within orbitals is what determines an atom's chemical properties, especially how it bonds with other atoms.
So now we're getting to the heart of chemistry. It's amazing how these tiny electrons with their wave-particle duality and fuzzy locations ultimately control how atoms interact with each other.
It all comes down to those electrons.
But how do we go from these abstract orbitals to the tangible world of molecules and materials?
That's where valence electrons come in.
Valence electrons, those are the ones in the outermost shell of an atom, right?
Exactly. And they're the key players in chemical bonding. They interact with other atoms, either sharing or transferring electrons to form bonds.
Like a little electron exchange program.
Haha, kind of. And depending on how those electrons are shared or transferred, we get different types of chemical bonds leading to all the incredible molecules and compounds we see around us.
So let me see if I've got this straight.
Mm.
Two atoms come close, their valence electrons start interacting, and depending on how they share or exchange those electrons, we get different types of bonds, which then determine the properties of the molecule.
You got it. It's all a delicate dance of electrons.
It's amazing how something so small can be responsible for so much complexity.
It really is. This electron dance is what creates everything from simple water molecules with their strong covalent bonds to the intricate structures of proteins and DNA.
We've covered a lot of ground here. We started with Thomson's discovery, then delved into the weird world of quantum mechanics, and now we're talking about the intricate dance of electrons in chemical bonding.
And we're just getting started.
Oh, I have a feeling we're just scratching the surface.
Next time, we'll crank things up a notch and explore how our understanding of electrons has led to some of the most cutting-edge technologies.
Like what?
We'll talk about particle accelerators and even the mind-blowing potential of quantum computing.
Wow, I'm already hooked. Can't wait to delve even deeper into this electron-powered universe.
It's going to be a wild ride.
Welcome back to our electron exploration. Last time we went from like electron 101 to how they behave in atoms. We even touched on that mind-bending world of quantum mechanics.
Oh, yeah. Things got a little weird.
A little. Ready to dive into some even more advanced applications of this electron knowledge.
Absolutely. It's amazing how something so small can have such a huge impact on cutting-edge science and tech.
So let's start with something I've always found super fascinating. Particle accelerators, like the Large Hadron Collider. These massive machines smash particles together at crazy speeds, right?
Yep, that's the basic idea. They're essentially giant racetracks for subatomic particles.
Oh, racetracks.
Yeah, designed to accelerate them to near the speed of light and then crash them into each other.
Okay, so picture this, a giant underground ring where particles are zooming around at insane speeds, eventually smashing into each other. So where do electrons fit into all of this?
Well, electrons are often used as probes in these experiments.
Probes.
Yeah, they're accelerated to these incredibly high energies and then smashed into other particles like protons.
Okay.
And by analyzing the debris from these collisions, physicists can get these incredible insights into the fundamental nature of matter and the forces that control the universe.
So it's not just about smashing things together for the fun of it.
No, it's much more than that.
They're actually trying to unlock the secrets of the universe using these collisions. And electrons are a key part of that.
Exactly. These experiments have led to some mind-blowing discoveries, like identifying brand new particles and getting a deeper understanding of the forces that shape our cosmos.
That's incredible. But I imagine it takes a lot to make these high-speed collisions happen.
Oh, yeah, it's not easy. One of the sources I read highlighted the massive engineering challenges involved in building and running these machines.
What kind of challenges?
We're talking superconducting magnets, ultra-high vacuums, and super precise control systems, all working together to get these tiny particles up to near the speed of light.
It's kind of mind-boggling to think about the level of precision and just pure ingenuity it takes to make these experiments work.
It really is a testament to human curiosity and our drive to understand the universe around us.
For sure. So speaking of pushing boundaries, let's move on to another area where electrons are playing a starring role, quantum computing.
Ah, yes, quantum computing. It's one of those topics that's incredibly exciting and a bit intimidating all at the same time.
I know what you mean. I know it has the potential to revolutionize computing as we know it, but it can get pretty complex.
It's true, quantum computing is still in its early stages, but the potential is enormous. So instead of using bits, which can be either a 0 or a 1, quantum computers use qubits.
Okay, qubits instead of bits. Got it. And what's so special about these qubits?
Well, here's where it gets really interesting. A qubit can be in a superposition, meaning it can be both 0 and 1 at the same time.
Wait, hold on. How is that even possible? It's like saying a light switch can be both on and off at the same time.
Haha, I know it sounds crazy. It all goes back to that wave-particle duality we talked about earlier. You see, in the quantum realm, particles can exist in multiple states at once until you measure them.
Okay, I'm starting to see the connection.
And quantum computers leverage this principle to do calculations in a completely different way than classical computers.
So they're using the weirdness of quantum mechanics to their advantage. Really clever.
Hmm.
But what kind of advantages are we talking about? What can quantum computers do that our current computers can't?
Well, they have the potential to tackle problems that are impossible for even the most powerful classical computers to solve.
Like what kind of problems?
For example, they could simulate complex molecules for drug discovery, optimize logistics and financial models with crazy precision, or even break the encryption that protects our online data.
Wow. It sounds like quantum computing could revolutionize entire industries. But you said it's still early days. What are some of the hurdles researchers are facing in building these quantum computers?
One of the biggest challenges is maintaining that delicate state of superposition in the qubits. They're super sensitive to any kind of environmental noise. Even the tiniest disturbance can cause them to lose their quantum properties. It's like trying to balance a spinning plate on a stick while walking a tightrope.
That sounds incredibly difficult.
It is. And another challenge is scalability. Building quantum computers with tons of qubits that can all work together reliably, that's super complex.
So it's not just about understanding the theory. It's also about figuring out how to build these machines that can actually put the theory into practice.
Exactly. It's a huge collaborative effort with physicists, engineers, computer scientists, and many others all working together to push the boundaries of what's possible.
It's inspiring to see how our understanding of electrons, these tiny particles, has paved the way for such groundbreaking advancements in science and technology.
It really shows the power of human curiosity and our constant pursuit of knowledge. But our deep dive into the world of electrons isn't over yet. We've explored their role in shaping our physical reality and driving technological innovation. But there's another layer to this story, a more philosophical one, that explores the interconnectedness of everything in the universe thanks to these tiny particles.
Oh, wow. I'm intrigued. Let's shift gears one last time and explore this deeper, more philosophical side of electrons. Welcome back to our final electron exploration. We've come a long way from the nuts and bolts of atomic structure to the mind-bending world of quantum mechanics, and now we're wrapping up with the philosophical implications of these tiny but mighty electrons.
It's been quite a journey.
Yeah, it really has. So we've established that electrons are everywhere, they're constantly in motion shaping everything around us. But what does that mean for our understanding of the world and our place in it?
Well, one of the key takeaways for me is this idea that electrons are like the invisible threads that weave the tapestry of the universe.
Wow, that's a beautiful way to put it.
They're the glue that binds atoms together, forming molecules and giving rise to the incredible diversity of matter that we see.
So we're not just talking about electrons as these tiny components within atoms. We're talking about them as fundamental to the very structure and existence of everything we know.
Exactly. And it goes even beyond the physical world. Think about how electrons are responsible for the flow of electricity powering our communication systems, our computers, the internet.
Yeah, it's true.
They're literally facilitating the flow of information and ideas across the globe, connecting us in ways that were unimaginable just a few decades ago.
It's like they're the unsung heroes of our interconnected world. These tiny particles constantly at work shaping not just our physical reality, but our social and cultural landscapes as well.
It really is a humbling thought that something so small, so seemingly insignificant, can have such a profound impact on our lives and our understanding of the universe.
You know, we often hear about the vastness of the universe and how incredibly small and insignificant we are in comparison. But this electron perspective kind of flips that on its head, doesn't it?
It does. We may be tiny specks in the grand scheme of things, but we're still part of this incredible cosmic dance, this intricate web of energy and matter that connects us to everything else in the universe.
We're all made of the same stuff.
Exactly.
It's a reminder that we're not just passive observers of the universe. We're active participants intricately woven into the fabric of existence thanks to these tiny electrons.
And that interconnectedness goes even beyond our physical existence. Think about the energy and information constantly flowing through the universe, carried by particles like electrons.
It's like we're all plugged into this massive cosmic network.
It is. We're all sharing energy and information in ways that we're only just beginning to understand.
It makes you wonder what other secrets these electrons hold. What other connections and possibilities are out there waiting to be discovered?
Absolutely. That's the beauty of science. It's a never-ending journey of exploration and discovery. And as we delve deeper into the mysteries of the electron, who knows what we'll find?
This has been an incredible deep dive. We've gone from the basics of electrons to the mind-blowing world of quantum mechanics and even explored the philosophical implications of an interconnected universe.
All thanks to those tiny little electrons.
Exactly. A huge thank you to all our listeners for joining us on this electron-powered adventure. We hope you've gained a new appreciation for these tiny particles that play such a huge role in shaping our reality and connecting us to the vastness of the cosmos.
Keep exploring.
Until next time, keep questioning and keep diving deep.